So we had done the unit step function, the exponential function. We're going to do one more. There's a bunch we could do. That sounds loud, doesn't it? No? It's good out there? So there's a thing called the unit impulse function. And it's a mathematical fiction because it's an infinite amount of force operating over 0 time. But you multiply the two together, excuse me, and you're getting an approximation to a really tall bump function that pretty much happens right at time t equals 0. And the function is called delta of t, unit impulse. And it's designed, in fact, it's defined by integrals, because you can't define a function that's infinitely tall and 0 width classically. And so it's just set up so that the area under it is 1. So that's property number 1. And if you multiply a function, another function, by the delta, and you integrate it, because it has an area of 1 and it's only exists at 0, you get the function at 0. Makes sense, right? Because the area is 1, it's only 1, it's only non-zero right there at time t equals 0. And so use these properties to Laplace this, because again, the function only exists under an integral. So it's going to pick off the e at time t equals 0. So the Laplace of the unit impulse is 1. So add that to a table of Laplace transforms. And because we want to Laplace transform differential equations, there's some theorems that have to do with that. All of these can be proved. We're not going to go through proving them all. But this is the basic list. So if you take the Laplace transform of a constant k times a function, if you think about that, we're going to stick a function f here multiplied by k, right, in the definition. Sorry, take away the dt, so here's the definition. Again, I'm not going to derive it, but the k can come outside the integral, because that's the property of integration. And so you end up with just the Laplace here multiplied by k. So that's what the theorem says, is that if you want to Laplace k times a function, you just pull the k outside the Laplace and then Laplace the function. And remember, this is what we call the Laplace of f, is the capital. Likewise, if you have the integral of two functions added together, you can split it up into two integrals added together. And so that means that the Laplace of two functions added together is the Laplace of each one individually. Because you can stick f plus g inside the integral, split it into two integrals, and you get and of course we call this capital F and capital G. Just that's our notation. So we want to be able to Laplace derivatives, because our differential equations have derivatives in them. And so you can derive that a derivative turns into s multiplying the Laplace. And then this is the initial condition. which is nice because we need initial conditions when we're solving differential equations. So there's where the initial condition goes in to the formula. If you want to prove that, you remember integration by parts that you learned in math? That's what this does. That's how you get there. Let me switch over to the other board here in just a second once you catch up. So this table of theorems is in one of the handouts on Laplace transforms I put on Blackboard. You can find it in there, along with a really nice Laplace table. If you want to do more than the first derivative, there's a formula that tells us how to do the nth derivative of a function. So you do s to the n, where n is the number of derivatives you do. And then you have a bunch of initial conditions that go with this. And you keep reducing powers of s and increasing the derivatives on the initial conditions. Until you get to s to the 0th power. So that's in the table of theorems. A good one to add that they didn't explicitly write out is the second derivative. And we'll use this quite a bit. So what does that mean? It means n is 2. Second derivative, right? So we got s squared times the Laplace of f. And then we got s to the 1st power times f of 0 minus s to the 0th power times f prime. Of course, s to the 0 is just 1. And so for a second order differential equation, remember we needed x and x dot initial conditions. That's where they go. Here's the initial position. And here's the initial velocity, if we're talking about a mechanical system. So if that's x. And that makes sense. If you want to know where the mass is going to go, you need to know where does it start out and how fast is it going at time 0. So really, these are the 4 basic ones that we need to do a differential equation, because a differential equation has terms added together. That means we can just split them up and do each one individually. You got numbers times the stuff, so you pull the number out, and this tells us how to handle derivatives. Notice that differentiation in the time domain is associated with multiplying by s in the Laplace domain. Here's one derivative, we got s times the function. Here's n derivatives, we got s to the n times f. So each derivative is associated with multiplying by s. Integration is the opposite of differentiation. So there's a formula that tells us how to Laplace an integral. But I think you could guess, if you think at what we do, if integration is the opposite of differentiation in the time domain, then what's the opposite of multiplying by s in the algebraic domain? Dividing by s, and that's exactly right. So if you have this integral of f from 0 to t, it's the same thing as Laplacing f and dividing by s. Often when we are looking at these systems, we want to know, well, what happens as time becomes large? Remember we did that with the mass spring damper system? We said, okay, if time becomes large, does this damp out to a new steady state value? What does it do? In the Laplace domain, there's a thing called the final value theorem that gives us that inside the Laplace domain. So we don't have to take the limit in the time domain, we can just do it in the Laplace domain. So this is related to t going to infinity, like we looked at in the time function. So if we want to know what happens to f when t becomes large, but we're in the Laplace domain, we can take the Laplace of that function, which we already have, multiply by s, and then let s go to 0, and we get the value. So this is really handy because often we'll Laplace the differential equation, we'll solve it, and instead of going back to the time domain, we just use this to tell us where it's going to end up. So this kind of stuff you've seen before, right? Differential equations, it's been a while. So this is a review, and again, the handouts are intended for you to read and remember how to do this. Because everybody's like that. You don't do something for a month or two, you got to go back and relearn it, but you learn it faster the second time or the third time. You guys caught up over here? Pretty good? All right, so let's go back to our example. The mass spring damper system, which we solved using traditional differential equations. Instead, we're going to solve it with Laplace transforms. So let's say we had, let's write it in differential form here. We had d squared first derivative plus 12 times the velocity, 25 times x equals f of t, the force. And that's where we plugged in e to the st for all the x's, and we solved and did the homogeneous solution and the particular solution, all right? So here's how you do that same thing in Laplace transforms. Let's see, we need to know our initial conditions. So what we're doing is that forced problem. Where at time 0, the step function kicks on at 25 for the force, and we're starting out at 0 position like that. So this is equal to that. So the Laplace of the left side has to equal the Laplace of the right side. So you Laplace both sides. And because we got this, plus this, plus this, we have to use theorem. Is that number 2, right? So that means we can Laplace each sum individually. And because we're multiplying by 25 and 12, we have to use theorem 1. And then when we Laplace the derivatives, we have to use theorem number 4, I think it was, right? Or was it 3? Yeah, we got to use 4. Well, we got to use 4 and 3. We're going to use 4 for the second derivative and 3. And then we'll have to use our tables to Laplace this thing. So we can write this up here. We're going to Laplace that. And that's going to be equal to the Laplace of this. And then we split this up. And I'm pulling the 12 out in this step. And the 25 we can pull out according to the theorem. Right? So that we applied the theorem for that. And then we have to Laplace the second derivative. So we have to go back to our notes and our theorem table. And that says that we get s squared. And we call capital X the Laplace of x. Here we get the second part. Oh, I jumped a step, sorry. I thought something was wrong. So we got s squared and x of s, and then we got the initial conditions that we got to throw in here. So x at 0, and then x prime, or prime is the same thing as a dot. It's the derivative. And so that's the first term, and then we got 12 times, this is the first derivative, so we get s times x capital minus x at 0. Then we got 25 times, and then x just turns into capital X, because that's just by definition, we're calling capital X the Laplace of x. So this thing is just capital X. And this is f of s. And I'm going to hold off plugging in the Laplace of this for right now. So let's figure out f of s here in a minute. So again, we're just Laplacing the first term, the second term, and the third term, and then the other side. So at this point, we stick in the initial conditions, whatever they are. I mean, this could be 0, or it could be a number, right? We could start it out at a position that's not 0, and then we just stick that number in here. For here, these are 0. So the initial conditions for this problem are 0. That is not always the case. That's because of these here. All right, so now we've run through our steps. We've Laplaced it. And maybe now we've lost sight of what we're trying to do. So the whole goal is to find the x, right? We want to solve this for x. That's what we want. We want to know the motion of the mass. So how do we solve this? Yeah, it looks like it's just algebra, which is the whole goal of Laplace, right? There's no derivatives anymore. So we have an x here, an x here, and an x here. So we just factor all those out. And then we divide by what we multiply by. We divide through to clear it out. So it's just algebra. So now we do algebra. And that's what makes this method nice for solving differential equations, because you don't have to think, okay, homogeneous solution, I know how to do that, but then particular solution, I gotta, well, what am I gonna try for the particular solution that might work and see whether it works or not? We just do this. It's just step by step by step, like cooking banana bread. Put the eggs in the bowl with the flour and the sugar and beat it and bake it. It's making me hungry. I need to make some banana bread. Okay, so we're going to factor out the x. And so that's going to multiply s squared plus 12s plus 25, and that's going to be equal to f of s. Still doing just algebra. Divide. So far, so good, right? In fact, there's the answer, as long as we plug in f. And what's f going to be? So f of t is 25, this unit step. So we need to Laplace that. Constant goes along for the ride, because that's theorem number 1. And then we have to go to our table and say, well, what's the Laplace of the unit step function? Because that's what we did. We turned the force on at time t equals 0. So we go back. What did we figure that out was? What did we figure that was? Yeah, when we did the integral, that's 1 over s. So you don't do the integral again. You just go to your tables and look it up. Which reminds me of a joke. See if I can remember it. So a mathematician, have you heard this one before? Mathematician, a chemist, and an engineer were given a red rubber ball and asked to find the volume. Have you heard this? Did I tell it in another class? So the mathematician measured the diameter and then used math, 2 pi times the diameter. There's a formula for the volume, right? So he calculated the volume. Graduated cylinder with water in it, and he saw how much volume was displaced, and he measured that, and he got it. So what did the engineer do? He looked it up in his table of red rubber balls. Because it's been tabled, right? There's a manufacturer that makes it. I guess to update the joke, you would Google the manufacturer and find the red rubber ball volumes for the tables. So we do this. We don't need to reinvent the wheel because it's already been done. A comment. Notice that in the Laplace domain, here's our input. And this is the response, or the motion, or essentially the output of the mass spring damper system. And so the thing that goes there in between essentially takes the input and gives us the output. In the Laplace domain, you take the input, you multiply by this thing, and you get the output. So people have called this something, they call this the transfer function, because it transfers the input to the output. And then we could even go so far as to draw block diagrams in the Laplace domain that illustrate that happening. F of s goes into this block and it multiplies times this, and we get the output x of s. Another thing to notice, does this polynomial look familiar for this problem? If you go back to the differential equation method, we got that polynomial. It was set equal to 0 to solve for the s values that made it work. Remember, e to the st, we plug it in, we ended up with that for the homogeneous solution. So the homogeneous solution is going to come from that thing. The transfer function. And then the input is going to give us the particular solution. So let's continue on with that. So let's go to the other board. We're going to plug in for f here. So that multiplies times that, and then we can figure out what x is. That's it, right? All right, do you remember where the final steady state value of this thing was? Back when we had our picture of the mass spring damper system. Starts out at 0, and we measure x over. Spring constant is 25, the damping is B, and the mass is 1. Yeah. Oh, yeah, I forgot to switch it, didn't I? Thank you. So this is where we multiplied by f of s. This is f of s there. Our damping was 12. Let me write that here. And we turned on a force of 25 at time t equals 0. So where did the math end up? Do you remember with the classical traditional solution? It slid over 1, right? So that the spring was stretched by 1. 1 times 25 balances out to 25. So we're 1 meter over. So that was the solution. How about here? Here's our answer. There's x. But it's in the Laplace domain, not the time domain. So to get x of t, we have to do what's called the inverse Laplace form. And that's essentially why there's no free lunch, is because this method's real straightforward and easy, but it amounts to about the same amount of work as the regular method because you got to do this step. But again, it's all cookbook. You just boom, step 1, step 2, step 3, step 4, step 5, and you're done. But we can shortcut this. What if I want to find out the limit as time gets large of x of t, but I don't want to find the x of t. I'm lazy. The final value theorem says multiply that thing by s. Right? So all I do is multiply by s. I'm just sticking it into the... So that's why that theorem is handy. And we're out of time, aren't we? So this is a good place to stop. Next time, we'll do inverse Laplace transform. Have a good weekend. The weather's supposed to be really nice.